your application seamlessly. Well, before that, I'll do a small quick intro into sequences. Sequences are basically unique numbers. They are ordered, are typically used as primary key for user IDs, order numbers, check numbers, etc. The key thing about sequence numbers here is they are generated by the database. Why? Because it's very hard to generate unique numbers on the application side. That's because multiple instances have to coordinate, and it's very hard to guarantee uniqueness and ordering when you have multiple instances in play. Let's look at the simple operations on creating and operating on a sequence. Create sequence is very simple. You can just call create sequence and give it a name. So here it's going to be S1. I'm going to use the same name in the demo too. To fetch the next value from a sequence, basically you just say select next val. Next val is a function that's provided by Yugabyte. It fetches the next number. And every time you fetch the next number, it'll be a new number. But if you want to see what's the current number that you retrieve the last fetch number, you just say select current val. So let's see how sequences are implemented and stored in a distributed database like YugabyteDB. The state of every sequence is stored in a special system table called sequences data. For fault tolerance, the state of the sequence is raft replicated just like any other row of any other table. This will ensure that even if the leader goes away, another follower will have the most recent state of the sequence. So here we have multiple applications. Multiple applications can fetch the value from the same sequence. Also, a single application can open multiple connections to the DB and fetch from the sequence. YugabyteDB acts as the coordinator to maintain the uniqueness and ordering of the sequence. As you can see, every fetch is a write to the table and has to be raft replicated. See, this is the leader here. This is it's just a single number. It has to be stored somewhere. And we store it in the table called sequences data, which is for that particular row, S1 here in T server 2 is the leader. This is just for illustration purposes. And you have two followers, and both the followers will have the data with from raft replication. But as you scale, this raft replication can become a bottleneck, and when a lot of instances are fetching from the same sequences. How do we avoid this?
And maybe before if you could just stay on one slide, the previous slide, I just make one comment that yes, sequences, because you have to coordinate and keep the state persistently, there is a slightly higher overhead fundamentally. And in this talk, of course, you'll see some of the mitigations to reduce that overhead. But it might be worth calling out upfront that if for your primary key, you never needed ordering to begin with, then you might be better off just using something like a UUID generator, which is like even lower overhead. It doesn't need to do any of this. But however, some applications, they don't want to use the UUID as their primary key. They want, suppose, their order numbers and so on to be dense, increasing numbers. Then they prefer to use sequences. And so I just wanted to give that little bit tangential context that it might, in a distributed system, if you can avoid using sequences, it's still a better practice. But if you did need to, then this talk is definitely going to be of interest to you because it talks about some of the ways to optimize the overhead of maintaining the sequence state. Yeah,
that's true. That's a very, very good point. I actually missed the mentioning about the UUIDs before. So basically, UUIDs are 128 bits long. You don't have correlation between two different UUIDs. There is another concept called ULIDs, which is lexicographically sortable. But still, if you have a high throughput system, you can get conflicts with that. So as Kannan pointed out, if in case you can avoid sequences, that would be great. But there are so many cases where you cannot avoid sequences. So let's see how to avoid this scaling problem. Connection level cache. So to avoid the bottleneck of multiple, the bottleneck that happens when multiple application instances try to fetch from the same sequence, that's because the primary bottleneck is because each update has to be raft replicated. To avoid this, Yugabyte offers connection level cache. Caching is a standard solution to avoid touching the database, writing to the database. But for sequences, uniqueness needs to be guaranteed and ordering. Let's look into this a little deeper. The connection level caching, right? Sequences are cached per connection. I'm going to explain that a little bit deeper. So this feature we have inherited from Postgres. The cache size can be specified during creation. In Yugabyte, by default, the cache size is 100. You can configure it during creation. And in Postgres, that I just want to point that out. For Postgres, the default size is 1. So every time you actually do an X value, you get an incremental number, 1, 2, 3, 4. So size can be altered. The size of the cache can be altered using alter sequence. And this is the default mode for Yugabyte. So how do we enable this? How do you configure this? So when you create the sequence, you can specify cache size. Right now, I have just shown you 100. Technically, you don't have to give 100 because that's the default size in Yugabyte. But if you want to have a higher number like 1,000 or 2,000, you can specify it right here during creation. And at the same time, you can modify it after creation too. So to have a G flag, we have a G flag that specifies the minimum guaranteed size for all sequences, YSQL sequence cache min-val. So also remember the cache size in Postgres is just 1. Let's see how a connection level caching helps in speeding up applications.
And before you go to the caching, there was a question that's come in which says, Raft replication is new to me. Does it guarantee strong consistency across servers?
So Yugabyte is a strongly consistent system. So consistency is a first-class foundational feature for us from day one. You have a couple of modes of a couple of algorithms to do consistency, like Paxos or Raft. Paxos is understanding Paxos itself is very hard. Raft is very easy to understand, implement, and debug. So our founders and founding engineering team, they have decided to go with the Raft. You can check out Raft. You have libraries on multiple languages. Raft is a very simple where you have multiple the peers in the whole system. They vote and then elect a leader every say about I think it's that's configurable, but by default about a minute or so. Any other question, Kannan?
No, we can keep going. Yeah. All
right. So the caching per connection. So as I said previously, when we fetched from the next val from the database, we every fetch was a write to the database. Here, when you have cache per connection, the first next val from a connection, remember, it's very connection specific. It fetches about 100 values because we have specified 100 to be the size of the cache. So each connection gets a separate cache with values populated from the actual table. For example, 1 to 100 here, it is 2 to 100 because the current value, this app, for this connection has already fetched one particular value. For example, before, let me also point out this particular red line. One thing to remember about caching is basically, if you have unused values in the cache, they'll be thrown away. They'll be discarded. They cannot be reused. That's because once you fetch some set of values from the table, the last fetched value is stored, and the database has no idea about how many values are used and how many values are discarded. There is also a reason, because you can alter the increment number, how the cache is incremented when you are getting the sequence from the using the next val. It can be altered later. So it doesn't make sense for the database to know about that information. So for example, if the connection uses only 20 values from the cache and does not use the remaining 20, that 321 to 400 is lost. I just want to point it out. But apart from that, so this particular app has its own cache, this connection has its own cache, this has its own cache. So every time you do a next val, it's fetched from the cache. It does not have to touch the leader or the database. There is no write operation. I'm going to show you those things in the demo. But as I said, when this cache is depleted, when the current value becomes 200, when you issue a next val after 200, then there'll be a write, which will be rapid replicate.
In other words, like basically maybe to summarize, if the cache length is 1, then every time the database gives a client a number, like suppose I get the number 1, it has to remember that its state has to advance to 2. Then when I get the number 2, it has to remember that the state has to advance to 3. And each of these remembering steps has to be raft replicated. Whereas what cache of 100 allows you to do is give a batch of numbers up front and advance the state from like 1 to 101, 101 to 201, kind of like amortizes the number of times the persistent state in the database has to be updated for this sequence. However, like Prem points out, if you gave a connection 100 numbers and it didn't end up using all the numbers, then you end up throwing away some unused numbers. And this may not be a big deal in practice because the sequence space is a big int, kind of like 2 to the power 64 or something. So there's like plenty of numbers, but that is the trade-off you're kind of making here. Yeah, go ahead, Prem.
Okay, let's see how connection cache will help you behave in a multi-region setup. So this is let's consider a situation where the database is deployed across multiple regions between US West, Central, and East. Let's say that you have your preferred leader set up in the East. That is our suggested deployment pattern. And you have an app running in US East. Now, the latency for the fetch from the cache is just going to be around 2 milliseconds. So it becomes probably even lesser because the app is going to be inside your region and maybe in a different zone than your T server. And from when it fetches from the cache, it's just 2 milliseconds. But when it refetches, it'll be 30 milliseconds. That's because of the raft replication. The reason is it'll write to this particular leader, and that leader will replicate to both the US West and Central. US West is 60 milliseconds away, US East is 30 milliseconds away. So this particular response will come faster. So it'll be the refetch will be around 30 milliseconds. Of course, this refetch will happen, repopulation of the cache will happen only once every cache size. Or in our case, it's going to be 100. Let's see what happens when you have applications deployed in other regions. So when in a multi-region scenario, when you have applications in other regions, other apps have to spend about 60 to 90 milliseconds for every next val when the cache is depleted. So when your sequence is in the cache, when the next val is going to be in the cache, then your fetch time is just going to be 2 milliseconds. That's still the same. But when you repopulate your cache, that is when your cache is depleted, it happens automatically. You don't have to do anything specifically, but the app will the database will take care of that. So when the current val becomes 300, and when you issue when this particular app issues a next val, then the refetch that it'll take a latency hit of about 90 milliseconds. Why 90 milliseconds? Because it has to, this connection, even though the app is connected here, it has to write to this leader here, S1. That is 60 milliseconds. And that has to be raft replicated to the closest server, which is 60 plus 30 is 90. So similarly, for an app in US Central, the cache, when serving from the cache, it's just 2 milliseconds, but the refetch will take about 60 milliseconds. So this could become a very big problem as every connection has to take a latency hit for cache repopulation. This could affect your scalability of the system. So how do we solve this problem? Any questions before we go to the?
Yeah, maybe I would say if the, when each connection runs out of the its sequence could be a little bit randomized, because over time, this connection may run out at a certain time, whereas on a different connection may run out at a certain time. So at least like it's kind of spread out, right? But one common challenge that can happen is if many app instances are being launched at the same time. Imagine that in order to scale up your service, you're launching like 100 new application instances, and each of these application instances is holding like 10 connections. So suddenly you're like launching 1,000 new connections, and everybody is going to try to reserve their cache range, right? And that's going to create a massive bottleneck on this single row, which is maintaining the state for that particular sequence, and all of those operations will end up getting sequentialized, right? So I think, yeah, it's both a problem on when cache gets depleted, but on connection startup time, where fundamentally all caches are empty, there is a larger bottleneck that we'll cover on how we have tried to address that.
That's a great point, Kannan. Thanks. Okay, let's see how you can avoid this particular problem when you have huge number of connections coming up and trying to refetch the cache. So we have Yugabyte introduces a new cool feature called T-server level caching. Let's see what it does. So with T-server level caching, the sequences cache is not per connection anymore. So every connection does not have its own cache. The sequence cache is per T-server. The cache is shared by all the connections to the T-server. The cache refreshes on depletion only once, right? Because if you have 1,000 different connections up to the server, when the cache is depleted, the refetch happens only once. For this, typically when we say, when we created the cache in the previous example, so we said that hey, cache size is 100 because now all the multiple connections are going to share the same cache. You want to give it a much higher number. Okay, to enable this, you have to turn on the flag called YSQL sequence cache method server. The default is connection. The connection caching is enabled by default with the same flag. This feature is available from 2.17.3. It's already in the master. You can check it out. Let's see how this feature could help you. So it's the same 3-node cluster that I showed you before. Multiple apps are talking to this particular node, and your S1, the leader for the row for that maintains a sequence state, is right here. So when multiple connections are made to the server, now instead of having a cache per connection, now there's a cache per T-server. It's the same T-server cache. Now, when this connection and this connection do a next val, they get sequential numbers from the same cache. So that's why you have 202 here and 203 here. So, so all the applications and connections to the same node share the same cache, only one right to repopulate the cache on depletion per node. And at the same time, so that is a limited Raft replication because you're going to have a bigger cache that is stored that is stored per T-server, and then all the connections to the T-server use the same cache. Let's see how this will help you in a multi-region scenario. So it's the same setup.
Maybe on the previous slide, maybe one other comment, like, so in this case, even if the app ends up restarting, you don't throw away your numbers.
That's a great point. I missed it.
Right. But if the T-server ends up restarting, and if that T-server had reserved a pool of sequence numbers, then those numbers will be thrown away. And our viewers might be interested in knowing that while Postgres's default caching mechanism is per connection, Oracle's default from very early days has been per server. And Oracle runs in a clustered mode too. People are aware. It's called Oracle RAC. Even in Oracle RAC, I believe the default caching is maintained at the per server level in an Oracle database. So this scheme that we are introducing kind of brings the sequence functionality similar to Oracle's sequence functionality.
I didn't know that about Oracle. Thanks, Kannan. All right, so in a multi-region scenario, now because the cache is per server, even though you have multiple connections talking to the same T-server, when the value is fetched from the cache, the latency is just 2 milliseconds. But when the refetch happens, it's still 90 milliseconds. That is not changed, but the repopulation of cache does not happen per connection. But it does happen for per T-server. So this can immensely improve the speed of your sequences in a multi-region setup. So I'm going to go into the demo and then show you how this actually works. So we have about 10 minutes, hopefully. Before we go into the demo, any questions?
That's good, Prem. Go ahead.
Okay. All right. So can you see my screen?
Yeah.
All right. So I just want to explain the setup of this window. So I'm going to have two connections here, one on this window, on this tab, and this tab. So these are the set of sequences that we are going to execute. And this particular tab is going to show the activity on the cache, when the cache is refreshed. Okay, first, I have a 3-node system. First, I'll show you. I'm going to connect to the first node. Servers. So it's a 3-node local cluster that I have set up. All right, so let me first create the cache. So I'm just explicitly giving size 100 just for illustration purposes, but actually I don't have to. All right. So as I told you, there is some activity on the server, and that was basically because it created the row in the sequences table, made sure it's after replicated. And I'm going to show you. Right. Okay. So now to get the next val from this particular sequence, all you have to do is select next val from S1. Now, because you see there was an activity on the table, that's because this is the first time you're fetching from the table. So that it had to be, the value had to be, it had to fetch 100 values from the table, and update that it has fetched 100 values from the sequence onto the row that maintains the sequence state. That is why there was a write. Now, when I do this next val again, there is no activity. You don't see any activity on the table. That's because it's already in the cache per connection. So I do multiple times, there is no activity. But let's say because I'm going to fetch about 100 numbers again, so that will cross the boundary of the cache, and let's see what happens. All right, so there was some activity on the table. That's because it fetched 100 more new values from the table, and that is why it had to write to the table, and which again was replicated. Now let's see how this caching works from another connection. I'm going to connect to the same node. So I have a shortcut for next val, so NV. So here, if you see, it gave me 201. But in this connection, if I do 106, but at the same time, I don't know if you noticed, probably I should have called out, when this next value was fetched, there was activity in this particular cache, right? So that was because it fetched new set of 100 values and then stored it in the cache. And every connection is going to do the same. Let me actually try to do it again. And then if I do next value,
so there is one question. Are there 3 servers and 2 connections in the above example? That's correct. There are 3 servers, but right now both his connections are to 127.0.0.1. So right now he's connecting to the same server, but because we are using the default per connection cache, you won't see it different. Each connection is reserving its own set of 100 numbers. Is that correct, Prem?
Yes, exactly. So I'll just quickly show you connecting to a different node. So this is to 127.0.0.2. So if I do a next value, it gave me 401. So that, and then you see that it fetched from the table. So this is a different connection. This particular tab is a different connection. It still maintains that sequence from because we fetched from more than about 200 items. So it's about 107.
Yeah.
Now that's it. So for every cache size hit, you will for the next val will actually touch the database. Outside of that, the next val will just be super fast, and it will just be the value will be fetched from the cache. To check the current value, you can do current val, just a shortcut. So I have the commands here. You can always look it up. So the current value is always going to be the same. Okay, now I'm going to show you how the server level caching is going to help.
So for the server level caching, okay, yeah, you're restarting the database with the.
Yes, I have to restart
by changing the sequence cache method G flag. Yeah.
Yeah. All right. So because let me show you now, the connection won't work because the servers were restarted. So I have to reconnect again. Now, because it's a new connection, the servers have been restarted. Let's see how the next val is going to go. Let me show you. Clear this. Very critical. All right. So there was some activity in the table. So what it is, if you remember, we fetched about 500 values in the previous example. Now the next val is 501. All right. Now, if you do next value, next value, next value, there is no activity on the table because it's still serving from the cache from the T server. Now let's see what happens when you connect to a different, the same node, not a different node, sorry, the same node, a different connection. When I do a next value, I get 505. See, because both these connections are sharing the same sequence.
Same T server, you mean? They're connected.
Sorry, same. They are connected to the same T server, which thereby they share the same sequence cache.
Yeah, they're basically both draining from the same T server level cache for that sequence. Whereas in the previous scheme, you would have gotten 601 or something on this connection, but now they're both sharing from a common pool of cache numbers at the T server level. Yeah.
Yeah. So actually, I have a way to actually show you what is. Okay, let's see. So I'm going to dump the sequences data table and then show you what value is actually stored in the internal database. So because when the last time when we fetched here, now we fetched 500 to 600 numbers. Now it has stored the number 600 here. So next time when because every time we fetched, it has updated the data here. So next time when we fetch, it'll store 700. So that's because our cache size is actually 100. Now this is fine. So this is the feature. Basically, you have two different connections connected to the same node, or multiple connections now connected to the same node. They share the same sequence. I'll just quickly show you what happens when you connect to a different node. So I just do next value. It's 601, but that's because they don't share the same cache. It's a different node. So maybe I can show you another connection opening to the same node too. So this is 602 and this is 601. That's because these two connections are sharing the same cache on node 2. That's it. That's pretty much it. That's the demo. Any questions?
Yeah, and I think fundamentally, to summarize, now you can imagine that maybe you have a 20 server database, but maybe you have like 5,000 connections starting up at the application tier, and they all don't have to. There can be a big startup problem, especially in a multi-region deployment, if they all have to reserve and become a bottleneck on the single row that's maintaining the sequence state. Whereas now you're kind of amortize the cost. Only these 20 servers are going to periodically refresh the sequence state that you need, right? Yeah, no, that was
when I fetch 100 more numbers, then your cache is going to be updated. So that's it.
Yeah, and the question, one more question was, for this configuration, is the cache size set at 100? But maybe you can cover that. The fact that the cache size G flag is common to both these schemes, right? And we didn't change that in this experiment. You left the T server cache size at 100.
So you can create. So is that what you want pointing out, Kannan? Yeah,
basically, like you remember in one of the slides you showed the connection method as well as the connection cache size min val. Assume you are not providing this cache size here, Prem. Suppose you just create sequence S2, right? Then the question is, what is the cache size? And I was just saying that the same G flag governs both the cache methods, whether it is connection method or server method.
Yes, it's the same cache.
If you want to just put up that G flag on the screen from your deck. You had a slide on your deck.
So this is the one. No, not this.
This is the connection method.
Yeah.
But remember, there's a cache size G flag.
Maybe I should have copied it.
It was in your deck, one of the slides.
Yeah. I'm going to... Yeah, this one.
Yeah. So
YSQL sequence cache.
Yeah. But it is worth making a point that for the if applications are using the server level cache, it may make sense to increase the default from being 100 to something like 1,000, because because you don't want every connection to reserve a very large number, but at the level of every server, it's probably okay to make this number slightly larger. Cool. Yeah, we are at time, and I think we've answered the various questions. I wanted to thank you all for joining us this week. There's another interesting topic on how Yugabyte handles high availability of transactions in the midst of failures. That's next week. But thanks all for joining, and see you again next week. Okay, there's one more question coming in. Maybe we can take it. How is the locking implemented within the cache? Is it a Yugabyte specific implementation? Yes, I mean it is. Yugabyte is open source. Is an open source project. You can see that in code. But yeah, fundamentally it is kind of a standard implementation to avoid like thundering herd and all that. Like if the cache is depleted at the T server, and if you have multiple outstanding next val requests, we make sure that only one of them does the heavier work of updating the sequence state and grabbing the pool of numbers, and then others share it. Yeah, it is sort of implemented, purpose implemented for Yugabyte, but in open source code. So yeah, thanks for all the good questions. Thank you, Prem, for joining us and covering an excellent topic. And over to you also for closing comments, Prem.
Thanks, Kannan. It was really nice. I mean, I just want to say one thing, for all the football fans out there, if you're watching Super Bowl next year, February, this feature will be in play. So that's the cool thing about this feature. It's a tidbit. And so if in case you have any questions, feel free to reach out. Okay, so feel free to reach out on Slack and check out our code base on GitHub. So I'm Prem and Kannan, by the way. Thank you.
See you all. Thank you.